So let's look at equations of state. An equation of state is a relationship between pressure, volume, and temperature of a substance. If it's a good description of this relationship, you can also use it to calculate any of these other energy properties, so internal energy, enthalpy, entropy, and there are others. We already know one equation of state. It's the ideal gas law, PV equals RT. Of course, not many substances are ideal gases, so there are others that people have developed. They're basically categorized as four separate sets of equations. The first of these are the virial equations. Virial equations are going to be purely theoretical. Empirical equations are purely curve fits to match data. Cubic equations of state are an attempt to expand the form of the ideal gas law to meet other non-ideal gases. And there's a whole family of those, but the van der Waals, Redlich-Kwong, and Peng-Robinson are the most common of those. And then we'll have the generalized equation of state, which is another attempt to generalize the ideal gas law for non-ideal gases. So first, let's look at the virial equation of state and the empirical equations, in particular Benedict-Webb-Rubin. So the virial equation, it's based on statistical mechanical theory. So it's purely theoretical, hypothesizing what would happen if we do this. The form that it ends up taking is Z being equal to PV over RT. Z is equal to 1 plus some constant over V plus a different constant over V squared, another constant over V cubed, and so forth. To truly match a real substance, you would need infinitely many terms. And these constants are called the virial coefficients. They are functions of temperature and functions of the substance itself. For many substances, B of T is well established. But unfortunately, it's only a very few substances that you can go as far as C or D, and it's very rare to have anything beyond those terms. So this is an area of study. These virial equations get better year by year, but for the most part, most working engineers are not going to find the virial equations very useful. But the empirical equation that is most often cited is the Benedict-Webb-Rubin equation. This one attempts to fit the virial equation to data. And it's been improved a little bit from this simple virial form, but essentially the Benedict-Webb-Rubin is an adaptation of the virial equation to fit real live data. Now, the good news is in your textbook, for several substances, you have the values of the constant for the constants that are required to use the Benedict-Webb-Rubin equation. In particular, page 933 for SI units, page 983 for engineering units, and you can find constants for butane, carbon dioxide, carbon monoxide, methane, nitrogen. The cubic equations of states are the ones that are probably most often used in simulation software. These are expanding on the ideal gas law to reflect the realities for why real substances are not ideal gases. So, for instance, one of the issues is that molecules are attracted or repulsed from each other. In an ideal gas, they just totally ignore each other. So if I want to deal with attraction of molecules, I need to adjust the equation. Another issue is that molecules in the ideal gas law are round and have no volume, while real molecules tend to be not spherical, and so I need to deal with that shape, okay, that's not round, and they take up space. Okay, the volume is not zero. And so to account for these things, we need to modify the form of the ideal gas law. Now, the first one of these cubic forms that was successfully introduced was the van der Waals equation. And this one has been around for a really long time, and it's not bad, okay? It's been improved upon, but it really isn't a bad starting point. And this also will be where we can see why they have the name cubic equations. Van der Waals basically said, well, the RT over V for P is equal to RT over V is okay, except for the molecules do not have volume 0, so to adjust for the fact that they actually take up space, he has a minus B term in here. They also have attraction for each other, and so the minus A over V squared term was added to account for the attraction between molecules. This is not used as often anymore. Later, it came about that Redlich-Kwong came up with something that was significantly more useful than this one for modeling real systems. And then the Redlich-Kwong was adapted to be further an improvement. Now, I said that the Van der Waals equation would be useful for seeing why this is a cubic equation of state. If you'll notice, we have one term has v squared in the denominator, and the other one has v minus b. If you were to clear this of fractions, multiply both sides by these common denominator, I would see that I'd have v squared times v minus b, which leads to a v cubed and lower order terms polynomial. So it's cubic in the variable v. And all the adaptations of the Van der Waals equation that are currently in use also have a cubic form. If I clear the fractions, it will be cubic in the variable v. Now, the two that are currently most often used are the Soave-Redlich-Kwong, usually just SRK equation, or the Peng-Robinson equation, PR. Okay? And these, you'll notice that they're similar to the Van der Waals equation, RT over V minus B. Instead of A over V squared, there's an extra term alpha that's a function of temperature and sphericity. Sphericity being how round the molecule actually is. And then in the denominator, instead of just V squared, I have a little bit of that contribution of the size of the molecule. Peng-Robinson is a different way of doing that. Both of them are very good. They're especially popular in the oil industry for modeling the systems there. Now let's look a little bit further at the Van der Waals equation. The data for this one, you can find values for some substances on pages 933 and 983 in your book. They'll have constants that can be used for A and B. But you can also estimate the constants just using critical properties, the critical temperature and critical pressure. And with this, I can make a huge improvement to the ideal gas law that is not all that much more difficult. If I'm using a computer, this is certainly easy. Now let's next look at the generalized compressibility chart. Now we've actually already done this in the earlier course, but it's time to come back to this. Remember, the generalized compressibility chart was the one where we had a graph of Z versus pressure for various temperatures. And what people found over the years was that no matter which substance, the graph had very much the same shape. And so you could squish and stretch those shapes so that they all lay on top of each other by adapting them to where the critical temperature and pressure, or the critical point, was on top of each other for every one of them. So that meant if you took the actual temperature and divided by the critical temperature, or the actual pressure and divide by the critical pressure, you can get these reduced temperatures and pressures, and one chart does a fairly decent job of fitting most substances. In your book, this chart is on pages 985 to 986. What we've been taught so far is that whenever Z turned out to be close to 1, we say that the substance is an ideal gas, and if it isn't close to 1, then we use this Z that we get that's not 1 to modify the ideal gas law. It goes on the temperature side of the ideal gas law. So PV equals Z times nRT if you're using total volume. If you use specific volume, PV equals ZRT. So that concludes our video on the equations of state.